Hello friends, welcome back to our YouTube channel Civil Stories. Here, you will find informative videos related to civil engineering. In the previous video, we had discussed about the theory of simple bending and the assumptions made in the theory of simple bending. Today in this video, we will discuss about the derivation of bending equation. The terms, factors which are used in the derivation of bending equation are neutral axis. The neutral axis of any transverse section of beam is defined as the line of intersection of the neutral layer with transverse moment of resistance. Due to pure bending, the layers above the neutral axis are subjected to compressive stresses, whereas layers below the neutral axis are subjected to tensile stresses. These stresses form a couple. Forces will act on these layers, whose moment must be equal to external moment m. The moment of this couple, which resist the external bending moment, is known as moment of resistance. Moment of inertia, a quantity expressing a body's tendency to resist angular acceleration, which is the sum of the products of the mass of each particle in the body with the square of its distance from the axis of rotation. Radius of curvature, the radius of a circle which touches a curve at a given point and has the same tangent and curvature at that point. Derivation of bending equation. Consider a small section of uniform beam subjected to pure bending. Due to action of bending on application of external load, part of beam length, dx will be deformed. Let r be the radius of curvature of beam or radius of neutral layer n'. Theta be the angle subtended at O, by a dash b dash and c dash d dash. Now consider a layer E, F at a distance of y. Below the neutral layer N, this layer will be elongated to E', F' after bending. After bending, the length of neutral layer N', will remain unchanged. But length of layer E', F' will elongate. Here, neutral layer is equal to unchanged neutral layer, which is equal to deformed length dx. For angle O, n'. Angle equals arc by radius. Theta equals n' by r. n' equals r multiplied by theta. Deformed length dx equals r multiplied by theta. Therefore, F equals r multiplied by theta. Similarly, for angle O, E', F', angle equals arc by radius. Theta equals E', F' by r plus y. E', F' equals r plus y multiplied by theta. Increase in the length of the layer F' minus E F r plus y multiplied by theta minus r multiplied by theta. That implies F equals y multiplied by theta. Strain in layer F, epsilon equals increase in length by original length, that equals y multiplied by theta by r multiplied by theta, that equals y by r. Since the radius of curvature, r, remains constant, strain in the layer is proportional to its distance y from neutral axis. As we know, Young's modulus equals stress divided by strain. That implies stress, sigma, equals Young's modulus, E, multiplied by strain, epsilon. Sigma equals to E, multiplied by epsilon. Sigma equals to E multiplied by y by r. Sigma equals to y multiplied E by r. Since stress is directly proportional to the distance y from neutral axis. Since both E and r are constant, stress, sigma in any layer is directly proportional to the distance y from the neutral axis. That implies E by R equals sigma by y, where maximum compressive stress will be subjected to topmost fiber, and maximum tensile stress will be subjected to the bottommost fiber. So far in this video, we have discussed, if a section of a beam is subjected to pure sagging moment, the compressive stress will be subjected above the neutral axis. The tensile stress will be subjected below the neutral axis. The neutral axis will not confront any stress due to applied external load. Stress developed at a distance of neutral axis, sigma equals to y multiplied by E by R. Consider a small layer at a distance of y from neutral axis. Let the area of the layer be delta A. Force on the layer equals stress on the layer multiplied by area of the layer. That equals y multiplied by E by R multiplied by delta A. Therefore, total force on beam equals integral y multiplied by E by R multiplied by delta A. That equals E by R integral y multiplied by delta A. But in the case of pure bending, no force exists on the section of the beam. Therefore, E by R integral y multiplied by delta A equals 0. Since E and R are constants, hence cannot be equal to 0, that implies y multiplied by delta A equals 0. We know that moment of any area about an axis passing through its centroid is also equal to 0. Hence neutral axis coincides with centroid axis. Centroid axis of a section also gives the position of neutral axis. As we have already discussed about moment of resistance, let M be the external moment developed due to the external load. We have force on the layer at a distance of y from neutral axis equals y multiplied by E by R multiplied by delta A. Moment due to force about neutral axis equals force on the layer into distance of the layer from neutral axis, y, equals y multiplied by E by R multiplied by delta A multiplied by y. That equals E by R multiplied by y squared multiplied by delta A. Moment of the forces on the section of the beam equals E by R integral y squared multiplied delta A. For equilibrium, the moment of resistance offered by the section should be equal to the external bending moment. M equals E by R integral y squared multiplied by delta A. Since I equals integral y squared multiplied by delta A, second moment of area or moment of inertia of section about neutral axis, M equals E by R multiplied by Im by I equals E by R. We know that sigma by y equals E by R. Therefore, M by I equals E by R equals sigma by y. This equation is known as bending equation, Bernoulli-Euler equation, or Flexural formula. Points to remember. The bending equation is M by I equals E by R equals sigma by y. Bending equation is used to find the stress applied on the beam. Deformation occurs when an unstressed beam is subjected to stress acting perpendicular to its axis. When the direction of force applied is perpendicular to the longitudinal plane of the beam, the upper layers of the beam are subjected compression while the lower layers of the beam are subjected to tension. Certain assumptions are made in the derivation of beam equations such as its straightness, cross-section, material homogeneity and elastic limit. That's all for today, friends. Hope you have found this video useful and informative. For more videos, Kindly subscribe to our channel and don't forget to press the bell icon to receive latest updates. Thank you.